Well, hello everyone. Just by looking at the title of this video that you clicked on today, you know we're going to be talking about electrical connections. And these electrical connections are going to be in regards to power walls, specifically my do-it-yourself power wall. And I think these things can apply to everyone else. And the reason why this I think is so important is twofold. Safety, first one would be safety, and the second one would be loss of energy. Okay, the better your connections, the less energy you will lose. Okay, now I have videos on this specific subject over the past 2 years. Okay, and the reason why I have videos on this is because I was, while in a process of building my power walls, the three that I have, I had to test certain things and see how they work. And while working on this, I have found many different things that work and many different things that don't work in regards to proper connections while doing your own power wall. Okay, now I'll go in the order of the videos that I made already, and there will be links in the description to see each one of these videos. I'm just going to mention them. I might put some overlay over what I'm talking about right now so you can see specifically what I'm talking about, but I think it's important to at least see parts of these videos. I'm not asking you to watch the whole thing, but parts of these videos, and see why this is important, as we will go into details of each thing. Now, the first video that I would like you to see, or see the part of it, and there are millions of different videos on a YouTube in regards to building a proper battery cable. This is just my way, and this is what I did in regards to my power walls. Okay, the first one will be a Powerwall 2.0 building battery cables. Okay, the next one, the second video in this series, will be LV5048 load and capacity test Powerwall 1.0 failed. Okay, the third one will be LV5048 balancer and BMS discussion, Powerwall 1 working again. The video number 4 will be LV5048 capacity test after repair. Number 5 will be cell test video, I failed. And sixth video will be LV5048 Powerwall 3.0 build video. Now, these are the videos that I posted online, and they normally show what I learned in regards to these tests. Okay, now specifically what I have done and repeated in all three power walls is stuff that I did in LV5048 Powerwall 3.0, the build video, at the minute 21:46. Go watch there and you will see what I did. I have repeated that throughout all three power walls. Okay, the only thing that I changed and what I corrected from before is I'm going to show you right now. Just give me 1 second. I'll bring it up over here. I'm back. So the thing that I use the most and I believe in is this silver conductive grease. Okay, try to show it over here. Okay, silver conductive grease. This is the thing that I used in regards to connections throughout the power walls and connections towards the inverters, including inverters. I have used this in assembly. This is actually conductive, not as much as you think, but it is conductive. Okay, so we will talk about this in the later part of the video. Okay, let's see what my power walls are doing in regards to connections on them. What kind of voltage drops we have, and what are those values calculated into resistance throughout those connections. and why I believe it is important to do this as best as you can, especially for us that are on these low voltage systems. I know some people don't think 51.2 volts is low, but in reality, it is really low. We would need to have something like as a car battery pack in our systems to have this working the best as it can without any significant power loss. I believe 400 volt system, DC volt system, would work the best in DC to AC conversion. If you guys ever remember the guy named Jack Ricard from EVTV, he was the proponent of using the 400 volt systems, 400 volt DC system, or specifically a Tesla battery pack in conjunction with an inverter that can handle that kind of voltage to create the AC. I believe in that too, and then there's a reason why the cars are at the 400 volt DC system, ones that are newer ones, and now we're going to even to the 800 volt system. But I wanted to mention that he was the proponent of that, and I really believe into that because you do not have to use a thick wire, the losses are less, and everything that comes with it. It's easier to have a higher voltage than a higher amperage without any significant power loss. That is actually my thinking. So let's go in the next step of the video. Let's calculate the stuff and see what kind of resistance I have through one Powerwall. All right, I have some footage of that at the different charging amp points, and let's see what's going on and what kind of a resistance we can calculate. So right now, this Powerwall is being charged at 22 amps. So let's check what the voltage drop is between these connections at this amount of amps flowing through the Powerwall. So okay, hold on, let's get down there. So at 22 amps, we have a 1.6 millivolt voltage drop across this connection. So only thing that we can conclude from here is that it's going to get higher once the amps flowing through the Powerwall get bigger and bigger as my solar production day goes on. So at this moment we are up at 28 amp charge for this Powerwall. Let's go down there and take a look at the same spot. Did voltage drop increase across that connection? Alright, here we go. So here we are on a connection between module 14 and 15, and current voltage drop at those 28 amps is 2 millivolts. Alright, right now we are at 41.7 amp charge on this Powerwall. Let's see what voltage drop is going to be. Alright, so we are at the same connection point between the modules 14 and 15, and the voltage drop right now is at 2.9 millivolts. As we can see, the voltage drop increases while charging amperage increases too. So at this moment we are charging this Powerwall at 55.2 amps, and then let's see what we have down there as a voltage drop on a connection between module number 14 and number 15. Hold on, let me just switch over here. So right now, connection between module 14 and 15, the voltage drop is at 3.9 millivolts. Alright, next part of this will be the main positive and the main negative up to the distribution block and the in the wireway right here. I'll open it up and we'll start counting those two. Alright, between main negative at the smart shunt and the main negative at the battery. At 56 amps, we have 100.7 millivolt drop. Imagine that. Okay, now we're gonna go to the main positive. For the main positive, it's at 69 millivolt drop between the main positive on the power wall and the distribution block. Now the 100 millivolt drop from a main positive up to the negative before the smart shunt, the reason for that is, guess what? BMS. So it's taking into the account the BMS, which is right there. There it is. So it's taking account the voltage drop across it too. So why are we doing all of this? Well, each voltage drop represents loss of energy that is supposed to go into your battery. These are, we can call them a parasitic losses, especially on the connections. Is that a lot? No, not really. I think my connections are really good. But over period of time, let's say 1 year, it will cost you a small chunk of energy that could have gone into your power wall and whatnot. So we'll continue once we have a full charge going on into the battery in the next about hour or so. So we are just about at the maximum over here of amperage being pushed through this power wall, which is around 67 amps. Let's see what the voltage drop is down on that same connection between 14th and 15th module. So let's take a look. Hold on. So right now we are at the 14th and 15th module. Again, let's see what the voltage drop is. And 4.9 millivolts at 67.5 amps. 4.9 millivolts at 67.5 amps. So it's really difficult to check these numbers again, but I'm going to check them again right now and see what we get. That will be off camera, and we will just use that to calculate the total voltage drop across the whole power wall. So at 67.3 millivolts, 67.3 amps, the voltage drop on the positive side between distribution block over here and a positive down on the bottom of the power wall is 84 millivolts, while the negative on the power wall through the BMS up onto negative side of this bus bar is 126 millivolts. So we'll use those numbers to calculate stuff later on. Alright, here we go. I'm done taking the measurements, and now we're going to talk about what we are going to calculate. Okay? The battery interconnects. Okay? One's with 3 cable and bus bar on positive and negative of opposing modules. There's 12 of them. 1, 2, 3 in each row, and there's 4 rows, and there's 12 of them. The single ones, which are 1/aught cables connecting the rows which are above each other or below each other, there's 3 of them. And then one giant connection from a positive here, main positive of the battery, to a main distribution block. There will be one measurement for the voltage drop, and then negative, main battery negative, including the BMS and all other connections, and that includes the switches too. That will be as a one other connection. There's one of those. I have measurement for that too. So we're gonna go and start calculating this. We're gonna be looking at it in a spreadsheet and see what kind of a number on the end do we get?
According to the Ohm's law, resistance is a value of voltage divided by amperage. So let's keep that in mind. So we got to come up with the resistance on each of connection points from a previous video segment. Okay, so the first one we're going to calculate is a negative connection, and that is a cable from a main negative battery connection to a negative battery side of the shunt. Okay, that includes a BMS and the bus bars. So on that one, the voltage drop across that connection at 67.5 amps is 124.3 millivolts. So let me fix this here. That's a little bit wrong. All right, 124.3 millivolts at 67.5 amps. In that case, the resistance of that point in the circuit is 0.00184 ohms. Okay, for the positive connection, and that's a cable from a main positive connection through on-off switch to distribution block up in the wireway, is 0.841 volts at 67.5 amps, or 84.1 millivolts at 67.5 amps. The resistance in that part of this circuit is 0.00124 ohms. All right. Now, the triple wire connections with the bus bars, okay, there's 12 of them. Okay, now per single connection at 67.6 amps, we do have 0.0049 volts or 4.9 millivolt drop, which in that case gives us a 0.000072 ohms of resistance per that single triple wire connection with the bus bars. We have 12 of them, which gives us a total resistance on all of those connections at 0.000864 ohms. Single wire connections with the bus bars give us 6.3 millivolts voltage drop at 62 amps, which equals to 0.00101 ohms, and totaling for all three connections at 0.00303 ohms. So the total resistance in this power wall, and that excludes voltage drop between the actual battery top, where the connection between that copper bus bar and actual aluminum connection on the cell, excludes that, is 0.004247 ohms or 4.247 milliohms. Okay, at 67.6 amp max charge that I achieved today per power wall, the voltage drop for one power wall would be 0.287 volts. Okay, now the voltage times amperage will give us a power. That will give us a total power loss on all of these connections in one power wall equal 19.407 watts. Now think about it. That's at 67.6 amps. Now we gotta guess some kind of power loss on average. I want to say that average power loss during all times of the day, and this is average, I want to guess that it's around 7 or 8 watts. Okay, guys. Now, let's introduce a little bit of a calculator over here. So, let's just pick a number. Let's pick a 8-watt number as a constant power loss through one Powerwall. Okay, constant power loss. Let's just say I'm going to pick 7 watts. Okay, if we have 7 watts times 24 hours a day, that equals 168 watt hours per day. Okay, that's power going in, power going out. Doesn't matter. Let's just say it's a 168 watt hours per day times 365 days. Okay, per 1 year, per one Powerwall, it will be 61,320 watt hours, or 61.3 kilowatt hour loss per Powerwall. We time that 3 Powerwalls, it gives us a total of 183.96 kilowatt hour loss per year on these connections. This is my calculation. I might be wrong. Tell me what I'm doing wrong. But I think we are losing on average around 5 days worth of power production every year on these losses in our Powerwall circuits. Now we come full circle around. This is why, going on further, I will advocate everybody to ask for higher voltage inverters. This will, in my belief, cut down on the power losses in the circuits, and it will let us utilize smaller, thinner wires, which will be less costly and less heavier in our solar system, or whatever kind of electrical system that you might be doing. So I'm thinking 51.2 volts or 48 volt system is inadequate. I think it needs to be 400 volt DC system, or let's say at least 200 volt system to have this working great.
So let's make some kind of a conclusion. Okay. You have seen, if you have followed this video from beginning and you have paid some attention to those 6 other videos that I made reference to at the beginning of this one, you will see that I have been proponent of this, right? And you have seen in the Powerwall 3.0 build that I did clean off every connection, and that I have cleaned every connection, and in each one of them I have included this silver paste for a better connection, to improve the connection, okay, and minimize oxidation. Now, what does this silver grease does? Okay, so okay, you have included, you have cleaned the connection, all right, you have smoothed everything out as best as you can. What does this grease do? Well, what this grease does, it's this microscopic particles of silver that are in this grease go inside those scuffs and fill them up. That way, increasing the surface area of the connection, thus providing for better conductivity. That's the whole point behind using this. That's the whole point of all of these connections that I made. I have come up with this solution, for at least for my system, to minimize the power losses seen in the previous segment. Now, why make this boring video at all? Well, I have seen many videos lately on a bunch of different channels where they start discussing this, and I always thought whoever does any kind of electronics should know and should be familiar with voltage drops or droops, or however you want to say it, and that everybody would try to do their best to minimize such problems in their circuits. And one more time, these are all low voltage systems. At this type of a power output that I have for my system, 51.2 volts is not enough. I think we should all have, in the next 5 years, we should all have 100, 200, or 400 volt systems that we can utilize. That way, the power losses at the higher voltages will be minimal compared to what we have right now. I really feel bad for the guys that have to use 12 volt systems, you know, drawing 200-300 amps through them just to achieve even a third or a half of the power that we have possible for the output here. Their losses are even more bigger than what we have. Okay, so guys, in the retrospect of this whole video, please have your connections good, have them nice and tight, have them clean, know what you're doing, try to do your best to make a best possible cables with the best possible connections. In the end, you know, that might prove the difference between the system catching on fire or, God forbid, doing something else. Okay, this is all about safety. This is a lot of power flowing through these 3 power walls. Please be safe, know what you're doing, and get your connections in order. A lot of videos out there talking about this, but yes, minimize the power losses and be safe. Minimizing the power loss equals safety. That's basically what I'm trying to say. All right, guys, you have a good one. And if you have any questions, please post them down in the comments, or any suggestions how to make this even better, and we'll go from there. Later, boys and girls.